So for this problem, we're going to be applying integrals to real life context. So we've got the integral from 1 to 4 of s of t dt, and we're saying that equals 12. S is the rate at which snow falls. So we're taking the integral of the rate. And t is hours after 5 p.m. So remember that an integral is geometrically area, right? This is area, right? So let's think about what area is. Area is base times height. Now, the height of this area will be S of t, which is inches cubed per hour. It's the rate that snow falls in inches cubed per hour. And then the base, the width, is dt. So that's the change in time. And so when we multiply our inches cubed per hour by dt, which is the change in hours, we end up with inches cubed. So the area under a rate, your time component kind of cancels out, if you want to think about it that way. And then you are left with your units of measure here. Okay. So if S is the rate that snow falls, then the integral of S of t will just give me the amount of snow that fell. Okay. And t is hours after 5 p.m. So if we start at 1, that's going to be 6 p.m. And if we end at 4, that's going to be 9 p.m. So remember that your bounds are going to be your independent variable. So that's time. So our bounds are in terms of hours as well. So a complete explanation would look something like this. The integral from 1 to 4 of s of t dt equals 12 tells us, and make sure that you always include 3 things. You're going to cut. You're always going to include context. You are always going to include units of measure, and you are going to include time. So always include context, units, and time. Cut. So the integral tells us the amount of snow. That's our context. That has fallen. And then look at your bounds from 1 to 4. So over 6 p.m. Actually, you know what? I think it's confusing to switch this. So this is what I'm going to do. I'm going to say over 1 to 4 hours after 5 p.m. I'm just going to go ahead and keep that, because I don't want to change like what t is. T is hours after 5 p.m. So I started writing this, right? I was like, okay, well, that's 6 p.m. to 9 p.m. But t is already hours after 5 p.m., so I don't want to confuse my notation here. So I'm just going to go ahead and keep it the way that it's written. So the amount of snow that has fallen over 1 to 4 hours after 5 p.m. And then what are my units? In inches cubed. I can actually be more specific, is 12, because we're told that the integral equals 12. So is 12 inches cubed. So I've included all parts of the problem, so double check when you're writing explanations. And by the way, this is not like a CPM thing or a Miss Bisagno thing. This is an AP style problem. Generally, on the free response part, there is one question where they will ask you to explain the meaning of something in the context of the problem. And it's very often an integral accumulation problem. So remember to include all 3 parts. Context. So I've got the amount of snow that has fallen. That's my context. I've got my time. Okay, 1 to 4 hours after 5 p.m. Notice that I used proper notation. Don't just write out 1, 2, 4. You need to use your interval notation in some way. And then I've got my units of measure here. I've got inches cubed. Now, if they didn't tell us that it was 12, then I would just say the integral tells us the amount of snow that has fallen from 1 to 4 hours after 5 p.m. in inches cubed. And I would just leave it general if they did not tell us what the answer was. But they told us the answer is 12, so I wrote 12. All right, so here is another accumulation problem, actually, we're given velocity and we're going to calculate the displacement after 2, 5, and x hours. So remember, displacement is the area under a velocity curve, and total distance traveled is area under the speed curve, or the absolute value of velocity curve. So we have 2t plus 5. We're calculating displacement after 2, 5, and x hours. So we're assuming that we're going to be starting at 0. So that's going to be the integral from 0 to 2 of v of t dt. So this will give us our displacement. Again, if it was total distance traveled, I would have to do this. But it's not total distance traveled, so I can just use it. We're going to include negatives and positives. So that is going to be antiderivative t squared plus 5t from 0 to 5. Plug in 5. 25 plus 25. Plug in 0. So I get 50. So that's the displacement. Oh, and we're in miles per hour. So we just get the displacement is 50 miles. Okay, 5 hours. I'm going to do the same thing. 2t plus 5 dt. I already have my antiderivative, but this time, oh, I just realized I switched. I just did this. I could remake this video, but I'm not going to, because now I already know that this will be 25 plus 25. I hope you caught that. So this one was 50 miles. Switched my bounds. Middle of the problem. Okay, so when I plugged in 2, I got 4 plus 10 minus 0, so that's 14 miles. There we go. All right, and then x hours, so 0 to x of 2t plus 5 dt is equal to t squared plus 5t from 0 to x. So that's going to be x squared plus 5x minus 0. And that would be also in miles. How far did the car travel between 2 and 4 hours? So this is not a great question because it's not super clear whether they're talking about displacement or total distance traveled. But because it says how far did the car travel between 2 and 4 hours, you know what? It doesn't matter because in this case, it's going to be the same. The reason that it's going to be the same is 2t plus 5 between 2 and 4 is already all above the x-axis. So my area will always be positive anyway. So in this case, my displacement will be the same as the total distance traveled because there is no negative area. All right, so I can just do the integral from 2 to 4 of v of t dt, which is t squared plus 5t from 2 to 4, which is 16 plus 20 minus 4 plus 10, which is 36 minus 14, which is 22 miles. So that was the distance traveled between 2 and 4 hours. And then lastly, why is s prime of t equal to v of t? So we know that this is in chapter 4. Okay, so we're just seeing, I was just checking to make sure, see how much we've gone over this. So we've gone over this quite a few times, actually, that the slope of position is equal to velocity. But let's talk about what velocity is. Velocity is, by definition, the rate of change of displacement. Actually, you know what? It's not rate of change of displacement. Let's be more specific. Velocity is the rate of change of position of an object. And I'm just going to put this in layman's terms. It's how fast in a direction, and I want to mention direction because velocity can be positive or negative depending on the direction. It's how fast in a direction an object moves. Okay, well, what's rate of change? Rate of change is a, actually, I'm going to change this a little bit as well. I'm going to say instantaneous rate of change. Instantaneous rate of change is, by definition, a derivative. Therefore, the derivative of position is velocity. Velocity is the rate of change of position. It's how fast in a direction an object moves. So by definition, velocity is the rate of change of position. That is the definition of it. And what do we call instantaneous rate of change? That's what a derivative is. So it's kind of like A equals B, so B equals C. So because velocity is the rate of change of position and rate of change is a derivative, then velocity is the derivative of position.